Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss approximating the derivative using the least squares best fitting polynomials. So in this topic we will describe or discuss how to estimate the derivative of data by using least squares best fitting polynomials, at least when the data points are being sampled equally in time. We will describe the formula for both linear and quadratic polynomials that are found with least squares. And for the quadratic polynomial, we will also look at approximating the second derivative. Now, suppose that we have found the least squares best fitting linear polynomial that passes through n equally spaced points. So they are sampled equally in time. Now, what we did before is we shifted and scaled the data so that the most recent sample is at 0 and previous samples are at negative integers. In the case where we were finding the best fitting least squares linear polynomial passing through 5 points, we found that the slope of the line was given by this linear combination of the y values. Now we have an issue here because we actually did do some scaling, because originally the time between samples was h. Consequently, the best approximation of the derivative is therefore a1, the coefficient of t, over h. All right, next, suppose that we found the least squares best fitting quadratic polynomial that passes through n points. Well, we've already found the coefficients for such a polynomial when n is equal to 5. And regardless of the other possibilities, we can always easily find those coefficients a0, a1, and a2. That polynomial has a derivative 2 times a2 times t plus a1. Now, at time t sub n, the most recent sample, the best estimate, therefore, is evaluating this derivative when t is equal to 0, and therefore it is a1. But remember, we scaled, so the time between samples is h. Therefore, the derivative is a1 over h. So a1 is the change per sample, while a1 over h is the actual rate of change in real time. Also, we can estimate the derivative in the vicinity of t sub n, and we can do so by estimating the derivative at t sub n plus delta times the step size, and the best estimate of that derivative is simply the derivative above evaluated at t equals delta, all divided by h to deal with scaling. More easily, we can also estimate the concavity. Just take the second derivative of the interpolating quadratic, that is a constant, 2a sub 2, and we divide that by h squared to deal with the fact that we have scaled our x-axis. Well, in this case, t-axis. So following this topic, you now understand how to estimate the derivative and the second derivative of data, assuming we have least squares best fitting polynomials for that data. You are aware that because our formula involves scaling, we must divide the derivative by the step size and the second derivative by the step size squared. And by now you should be aware that if we already have the coefficients a0, a1, and a2, then we can find these estimates in order 1 time. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!